What's the idea behind Riemann sum? First of all, let us discuss area problem. The area of a region with a curved boundary can be approximated by summing the areas of a collection of rectangles. Using more rectangles can increase the accuracy of the approximation of the area. So consider the following curve. If you use some rectangles, 2, 3, 4, 5, and so on, you get some approximations of this area below the curve bounded between the curve and positive part of x-axis. As you can see, if you increase these numbers of rectangles, you get a better approximation. So our goal is to increase these rectangles, but at the same time, you see the width of rectangles are getting smaller and smaller. That's the idea of Riemann sum and finding the limit of the Riemann sum and defining definite integral. Let us use rectangles to estimate the area under the parabola y equals to x squared from 0 to 1. So this is the visualization that we have. We have y equals to x squared, x is bounded between 0 and 1, and then you plug in 1 into the function, you get the height equals to 1. Suppose we divide S, which is the area below the curve, bounded by positive part of x-axis and this vertical line to the origin by 4 strips, S sub 1, S sub 2, S sub 3, and S sub 4. So basically dividing this into 1, 2, 3, 4 pieces. Please note that on the horizontal line, these lengths are all the same. For now, we're going to introduce 2 different methods of calculating or approximating the area. Between 0 and a fourth, we want to calculate this little area bounded on the subinterval 0 to 1/4. To calculate this little area, you basically need to find the width and multiply by the height. The width is just 1/4, and the height is 1/4 to the second power. So the area of this small rectangle is 1/4 times 1/4 squared. Now, if we form another rectangle and calculate the area of this rectangle is on subinterval 1/4 and a half. To calculate the area of this rectangle, the height of this rectangle is a half to the second power. So this little area is 1/4 times a half to the second power. Now let us take a look at our third rectangle. It is located on subinterval a half and 3/4, with the height equals to 3/4 to the second power. Again, to calculate the height, we can just plug in 3/4 into the function and calculate the height. So the area is 1/4, which is the length of this subinterval, times 3/4 to the second power. And the last rectangle is this rectangle here. I know you're wondering why we are using these rectangles, why we get a larger approximation. This is one of the methods. We're using upper area. So this rectangle is located on subinterval 3/4 and 1. To calculate the area of this rectangle, we need to find the height, which is basically 1 to the second power. So the last area is 1/4 times 1 squared. Please note that all of these subintervals, they have the exact same length, 1/4, 1/4, 1/4, and 1/4. They have different heights because the height of this rectangle is different from the height of this rectangle. The height helps us to calculate this little side. So the multiplication, as you remember, gives you the area of the rectangle. So if you do the calculation, you get an approximation of 0.46875, which is a larger approximation than this area. Another method that we're going to introduce is taking smaller rectangles. Now, we are using basically 4, but this guy here with height 0 is just located on the horizontal line. On the very first subinterval, the height of this rectangle is 0. So 0 squared, which is 0. To calculate the area of each rectangle and adding them together, it is basically 1/4 times 0 squared, which is the area of this rectangle here. The second rectangle is located on the subinterval 1/4 and a half with height 1/4 to the second power. So this guy is going to be 1/4 times 1/4 to the second power. Let us calculate the area of the third rectangle, which is located on the subinterval 1/2 and 3/4 with the height 1/2 to the second power. So you get the third area to be 1/4 times 1/2 to the second power. And finally, the last one is located on the subinterval 3/4 and 1 with height, which is 3/4 to the second power. If you add the last area, 1/4 and 3/4 to the second power, you get a smaller approximation, which is now 0.21875. So this is the idea of Riemann sum. We're going to add more rectangles and get a better approximation. So far we saw that if we just divide this up into 4 sub-areas, the area of S, which is below x squared and positive part of x-axis and vertical line here, and the origin is bounded between 0.21875 and 0.46875. To get a better approximation, as we mentioned before, we need to increase the number of rectangles. If you do that, the width of each subinterval, in this case, is 1 minus 0 divided by n. Then you take the limit and calculate the integral. So in general, if you want to calculate the area below this curve, what are you going to do? You are going to form subintervals. The starting point, x sub 0, is a. Then the distance between the very first point and the second point is delta x. The distance between x1 and x2 is delta x. So please note that the length of each subinterval is delta x and x sub n. The last point stops at b. We are forming a regular partition. Suppose a to b is a closed interval containing n subintervals, x sub 0 to x sub 1, x sub 1 to x sub 2, x sub 2 to x sub 3, and x sub n minus 1 to x sub n. They have equal length, which is denoted by delta x, which is b minus a, divided by n, with the starting point or initial point x sub 0 and the terminal point x sub n. The endpoints x sub 0, x sub 1, x sub 2, x sub n minus 1, x sub n of subintervals are called grid points. They create a rectangle partition of the interval a to b. In general, the kth grid point is x sub k, which is a plus k times delta x. So now that we calculate each width, we need to find the height, calculate the area of each rectangle, which is f of x sub k star. X sub k star is a point in the subinterval times delta x. And remember that delta x is b minus a divided by n. So in the next slide, we summarize everything. In the kth subinterval, x sub k minus 1 to x sub k, we choose any point x sub k star and build a rectangle whose height is going to be f of x sub k star, the value of f at x sub k star, which gives you the height of your rectangle. Then the area of the rectangle on the kth subinterval is the height times the base, which is f of x sub k star times delta x. Now, summing all of these areas together, we obtain an approximation of the area of R, which is called the Riemann sum. F of x sub 1 star times delta x plus f of x sub 2 star times delta x plus the rest of the terms plus f of x sub n star delta x is a Riemann sum. If you take the limit as delta goes to 0 or as n goes to infinity, this is denoted by definite integral between a to b of function f dx. So this is the idea of Riemann sum, but we have different methods calculating the Riemann sum using the left-hand sides or right-hand sides or the middle values to calculate the Riemann sum.